Okay, people, objective 56, our second to last objective of the year. We're going to finish strong here. So we're going to talk about similar figures. And what I want you guys to remember about similar figures is this idea of what we call proportionality. Maintaining proportions when you scale a figure to be bigger or smaller. You're maintaining certain proportional dimensions. And we'll see what that means. So let's just follow through on a couple proportions here. Let's make sure, let's do a little warming up with these here. Let's get our pen going. All right, so we know that our strategy, we can always cross multiply. So we're going to cross. 3 times x is 3x. 7 times 12 is 84. Solve for x. X is 28. Same thing over here. Make sure that we put our variable here in parentheses. So now we cross multiply. We get 12 times parentheses x plus 3 equals, I don't know this one off the top of my head. Wow. That should be an equal sign. Sorry about that. 19 times 54 looks to be 1026. If my pen will ever function again. Okay, so we got to do a little distributing. 12x plus 36 equals 1026. Let's get that x term by itself. 12x equals 990. And we got to solve for x. Divide both sides by 12, which again, I got a handy dandy calculator, 82.5. Okay, so getting back into proportions, they're going to come back up in this objective and the next one. So that's why we're warming up with them here. Okay, the thing with similar figures is first we need to define what they are, and we're going to try to relate them to something we know, which is congruent. So if you want to draw two congruent figures, and a lot of times, I don't know, I like to draw rectangles or squares. Congruent figures. Boom. How do we know they're congruent? Well, because they look exactly the same, and we know that. So congruent, anybody can draw two congruent figures because you just repeat the same exact thing. So congruent is same shape and the same size, same exact size. So if we drew in these tick marks, it would be this and this is equal, this and this, this and this. They're all entirely congruent. They're exactly the same. Now with similar figures, it's going to look something a little more like this. So there's kind of this scaling going on here. And the thing with similar figures is that they're the same shape, but they're a different size. And when I say shape, guys, I don't just mean that they're both rectangles. We have to kind of transition our idea of the word shape from the very basic sense of just like triangles and circles and squares and rectangles. Shape means that it holds certain dimensions. So when we say the same shape, we mean that it maintains the same proportion of its dimensions if you kind of scale one down or make one bigger. Okay, so they're the same shape, but they have different size. That's what it means for things to be similar. So for example, look at these two triangles. You can kind of tell they hold the same shape. Not just that they're triangles, but it's kind of if you scaled one down, it holds the same distance between some of the sides. Like it looks as though they are just kind of shrunk. One is a shrunk version of the other. So when we talk about similarity statements, here's the symbol that we use. It's just this, I believe it's called a tilde, and it's the thing that actually comes above the congruence symbol. But anyways, so it's not an equal sign. We use this kind of curvy sideways, S or number 2. So, excuse me, what we're saying is that if in the big triangle, we are starting at T over to F, then back to S, in the small triangle, we're going to do the same order. So we start at the top with A, we go over to the right side with W, and we come back to the left with N. Okay, let's think of another way that we can name this. Let's name the triangle FTS. If we name the big triangle FTS, we start on the bottom right, we go up to the top, and we come down the left side. So if we want to make this a similarity statement, we're going to need to make sure we start on the bottom right, go up to the top, and come down the left-hand side. So it's the same idea. Order matters. Order is really what matters here. Okay, so very similar to congruent statements, we just need to name the triangles and shapes in certain ways. So we got 3 quick examples here. So why is a similarity statement important? Because of the same exact idea. The order of the letters is what tells you where the similar sides exist. The order matters. Okay, so for example, right, A, B, C, D, E, F, the hexagon corresponds to Q, R, S, T, U, V. So even though A is up here in the first position, because it's the first position here, it's not S. So apparently this hexagon over here has kind of been twisted around a little bit. So Q is really the one that starts in first position, and then it goes around in order, Q, R, S, T, U, V. Okay, so which side in the second hexagon, so we'll call this hexagon 1 and this hexagon 2, so which side in the second hexagon corresponds with the 13 centimeter length side? So I believe we were told on your note sheet, you were told that BC is equal to 10 and then ED is equal to 13. So now we've labeled it over here. So this is the side that's labeled 13. It connects D and E. So what I want us to do is go to our similarity statement, and we go and find D and connect it to E. So that connects the 1, 2, 3, fourth letter to the fifth letter. So since the order matters, we need to do the same thing over in the second hexagon. Go connect the fourth to the fifth. So let's count 1, 2, 3. This the fourth to the fifth. So we want to find the side TU, and that's what we're going to label 17. So TU is going to be 17 because they are the letter pairings that connect position 4 to position 5. And we have to keep those consistent. Okay, the second thing, it says which side in the second hexagon corresponds with the 10 centimeter side. So the 10 connects B to C, which is positions 2 and 3. So we need to go find the hexagon that connects 2 and 3. So that would be R to S, and we will label that 14. So that's why the order is so important. It helps us determine which letter positions to connect to make things similar. Okay, this next one is all about this idea of keeping the proportionality. So we're going to have 2 rectangles. They are similar, so we are told that they are similar, which means that one of them is just a shrunken version of the other. Determine the width of the smaller rectangle. So this is where proportions come in. Guys, when this says that the 2 rectangles are similar, it means that they have to hold the same proportion of dimensions. So whatever the big rectangle, so the big length over the big width must be proportional to the small length over the small width. So we're going to call this length and this width, and this is length, and certainly we have width. So we can compare big to big is the same as equals small over small. So we're going to go big length over big width needs to be the same proportion as small length over small width. All right, so here we go, big to big. 16.1 over 10.12, and that needs to be proportional to the small length of 7 over the small width. Big over big, same proportion as small over small. All right, let's do our cross multiplying. 16.1W is equal to 10.12 times 7, so 70.84. And then we go and divide by what's in front, and we solve for W dividing by 16.1, so we get 4.4. And guys, this should make sense because think about it. In the big rectangle, the length is larger than the width. So in the small rectangle, the length also needs to be larger than the width. And it sure is. 7 is bigger than 4.4. So that's what we mean when things have to stay proportional. All right, last example, because 56 is pretty quick. And they kind of go together, but I'm going to stop it at 56, keep it separate, and then I'll make a different one for 57. Okay, hexagon ABCD EF is similar to hexagon GHIJKL. Find JK to the nearest tenth if we know that side DE is 14, EF is 17, and KL is 10. So first thing we want to do is go and label that. So first of all, I'm going to put the big hexagon and the small. So where's DE? DE is 14, EF is 17, and KL is 10. Okay, and we need to find JK. So JK is going to be, we'll put an X here. Okay, so what I want us to determine here is which sides match up. GHIJKL. And when you put them on top of each other, guys, it's really easy to see. So DE and JK match up because they connect positions 4 and 5. And then EF and KL match up because they connect positions 5 and 6. So here's what we're going to do. Is in order to make sure that we're keeping the same proportion, we're going to go the big triangle that connects 4 to 5 over the big hexagon. These aren't triangles. The big hexagon that connects 4 to 5 over the big hexagon that connects 5 to 6. And we need to keep the same proportion, the small hexagon that connects 4 to 5 over the small that connects 5 to 6. Okay, so the big hexagon that connects 4 and 5 will be DE. So we have DE, which is 14, over the big that connects 5 to 6, so that's EF. So that'll be 17. The small one that connects 4 to 5 is going to be JK. So that's X over the small one that connects 5 to 6. So that is KL, which is 10. Do our cross multiplying. 17x equals 140. Divide by 17. We get 8.235. To the nearest tenth, we get 8.2. So you have to make sure that you are making a proportion that follows the same pattern. If you're going to do the big over big and small over small, you need to make sure you do the big side that connects positions 4 and 5 over the one that connects 5 and 6, and you need to do the same pattern with the small hexagon as well. Okay, so we should be good for 56. See you back here in a second to start on 57. Wait a minute. Okay, cool.